Okay, Chapter 2, Motion, Part 1. Motion. We say an object moves if the object changes its position in a given time interval. That is, if the object is at one point in space at one instant of time and a different point in space at another instant of time, we say the object is in motion. Speed of a moving object is the rate at which it covers distance. So in words, speed equals distance divided by time. This is the simplest equation that we will get, and you will learn how to use this equation. And to keep from having to write these words every time, we will use symbols for these quantities as time go on. So, as an example, suppose you move a distance of 60 miles in 2 hours. There's, that's an average of 30 miles per hour. That's not the instantaneous speed. That's the average speed, 30 miles per hour. As a second example, if you move 24 miles and do that in a half an hour, then your average rate of motion is 48 miles per hour. Instantaneous speed now. Instantaneous speed is an object's speed at a given instant of time. That is the speed that your speedometer reads on your automobile. It's the instantaneous speed. As you accelerate or as you slow down, you get a reading on the speedometer. That's your instantaneous speed. So learn this phrase, instantaneous speed. Okay, go on then. And so here's an illustration of this. Okay. Now, there are two types of physical quantities that we will encounter. One is the scalar quantity, has magnitudes only, such as time, mass, speed. There's no direction associated with these quantities. The other type quantity that we encounter is called a vector quantity. And it has, or they have, because there will be many of them, have magnitude and direction, such as velocity, acceleration, force, momentum, etc. A vector can be represented by an arrowhead line whose length is proportional to the magnitude of some quantity and whose direction is that of the quantity. So the arrowhead points in the direction that the vector is in. Here's an example of an automobile that is moving from left to right. It is shown to have a instantaneous velocity vector pointing in the same direction that the object is traveling in. Adding vectors. We have to account for the magnitude and direction when we add vectors, and you will see that there's a graphical way of adding them, and we place the tail of one vector at the head of the other. And in this case, let me now show you one important case of the use of the Pythagorean theorem. As you recall, it is an equation excuse me, that involves a right triangle. Here's one side of the right triangle is length A, pointing from top to bottom, and the other vector B pointing from left to right. But C then is the resultant of adding in a vectorial manner vector A and B. It turns out then that with the use of Pythagorean theorem, we can find the length of C if the length of A and B are known. Here is an illustration of that. So it turns out that if A in the previous slide was 5 kilometers and B was 3 kilometers, it turns out if you go through the math here and take the square root of 34, you get 5.83 kilometers. The square root of a kilometer squared is a kilometer. Okay, so the square root address the numbers and the unit, the kilometers. Acceleration now. This will be represented by the lowercase letter a in all that we do in this course. The acceleration of an object is the rate of change of its velocity, and it is a vector quantity. Once again, the acceleration of an object is the rate of change of the object's velocity, and it is a vector quantity. Well, now let's see some equations that we can relate other quantities to the acceleration. For an object moving in a straight line motion, and that's the only kind we will consider in this class, and it's moving with constant acceleration, we have this mathematical relationship that the acceleration A is equal to the final velocity of the object minus the initial speed of the object divided by the time t. This is an equation that we will use a great deal, and it gives, so if you know any three of these four quantities, 1, 2, 3, 4, if you know any three of them, this equation allows you to find the fourth of them. Okay, here's an illustration. A car accelerates from 15 meters per second to 25 meters per second in 20 seconds. So without saying it in actual words, the initial speed is 15 meters per second. That's v sub I. The final speed during this time interval is 25 meters per second, and the total time is 20. So 25 meters per second minus 15 meters per second divided by 20 seconds, you go through this math, and you get an acceleration of 0.5 meters per second per second. And a meter per second is effectively a meter per second squared. So it's not like the seconds get canceled, the seconds get squared. That's the standard unit of acceleration, and we'll see that quantity over and over again. This is one way, or this is another way. So as I said, if you know any three of the four of these, you can find the fourth. Here then, if the top equation is true, so is the middle one. Vf is equal to Vi plus A times T. So when you have two quantities juxtaposed in this manner, juxtaposed mean attached next to each other. So when you have two that are juxtaposed, it means to multiply. So you don't need the old time sign. Just putting them adjacent in this manner or juxtaposed in this manner, it means to multiply. Often though we use 2 to represent final and 1 to represent the initial, so the latter equation is the same as the middle. This is another example here. A car whose brakes can produce an acceleration of a negative 6 meters per second squared is traveling at 30 meters per second when its brakes are applied. What is the car's speed 2 seconds later? And what is the total time needed for the car to stop? You can make this calculation. At the end of that 2 seconds, it's going 18 meters per second. And how long did it take for all this to happen? It is equal to a negative 30 meters per second divided by minus 6 meters per second, 5 seconds is the time that it took. Okay. Acceleration then, as we say, if we know the initial velocity, the final velocity, and acceleration, then we can also determine how far an object travels in a given amount of time. One more equation, and this is the equation here. Distance for d is distance, is v1 times t plus 1/2 at squared. We didn't just pull this equation out of the sky. It is a derived equation from the previous two equations that we've dealt with. So if v1 is equal to 0, then the equation simplifies 1/2 at squared. Let me illustrate this. Accelerate. Okay. Let's look at this situation here as well. Watch this situation now carefully. The object moves faster, faster, faster. Now it's going to be an even faster rate of change of speed. It has a higher acceleration. Okay, that's what I want you to see. Okay, so once again then, if you know these quantities already, v sub 1 equals 30 meters per second. If the acceleration is a negative 6 meters per second squared and t is 5 seconds, the total distance traveled is 75 meters by that mathematical equation. Falling, just say a word about falling. When an object falls in air where the air resistance can be negligible, the acceleration due to gravity is a constant. And it was Galileo who first observed this, and he's credited with understanding this kind of motion. The speed of a falling object depends on the time, not on the object mass. And as I said earlier, if you neglected air resistance, all objects fall at the same rate. And that rate turns out to be 32 feet per second squared, or 9.80 meters per second squared, or 981 centimeters per second squared. Okay, this is an illustration of a falling object. This is the equation that's needed to illustrate this kind of motion. Okay, that's all I want to share for in this presentation. Have a good day.